Okay, so just a couple examples that we didn't get to yesterday. So we were looking at this definite integral, right? We're adding up the area under, and the integrand has two parts to it. Sine x minus 2, so we're looking at the area under that curve from negative 7/2 to positive 7/2, negative 7/2 pi to positive 7/2 pi. So what I want to show you here is that when we break this thing up into pieces, right, we can split this into two separate integrals. I've got the integral of sine x over those limits minus the integral of 2 dx over the same limits. We can really take advantage, because they're symmetric limits of integration, we can take advantage of those properties we talked about yesterday, right? So what we'd want to do, remember, if we go back to our properties that we had looked at, if we have an even function, then the
Third one
down, where are we here? Right here, third one down. For an even function, an integral over symmetric limits is just 2 times the integral of the function from 0 to the upper limit, right? So that simplifies things a little bit, but even better, if it's an odd function, any definite integral over symmetric limits of integration is always 0. The positive and negative areas cancel, right? So we want to know then for this function, is sine x even or odd? Okay, and that's kind of where we left off. So there's the question. Because if it's an odd function, what's the answer to that integral? 0, right? So it'd be nice to know if it's odd, so I don't have to do any work, right? So what's the answer from last year in pre-calc? 1. Yeah, right? Remember that from last year? So we know that sine of negative x is just negative sine x, isn't it? Right? And we can tell that from the unit circle. Man, the unit circle does everything for you. It's so good.
Especially in tau.
Especially, of course, especially in tau. So if I go forward some angle x, and I'm at that point right there, right? Well, what if I go down negative x, right? So if I'm taking a sine of negative x, I'm just going backwards x from the starting point. Yeah. Notice that the y values are opposites, aren't they? Right? At this point right here, what are the coordinates? Well, the coordinates are going to be positive cosine x, positive sine x. What are they going to be here? I'm still going to go cosine x to the right, but I'm going to go sine x down.
Negative sine x.
Right. So you can see. So you can see that, yeah, it's an odd function, right? And you can also see that by just looking at its graph. Right, what's a sine function look like? Well, sine function looks like that, doesn't it? So it clearly has rotational symmetry about the origin, right? So we can see right away then that this one goes to 0 because of that property, right? What about 2?
It's just a constant.
Okay, but is it even or odd?
Number.
Doesn't matter that it's an even number. What matters though, where we get the word even and odd, it's, it just kind of stuck, but even and odd refers to polynomials and power functions. So if you're looking at a power function or a polynomial that has only even powers of x, it's guaranteed to be even. If it has only odd powers of x, it's guaranteed to be odd. Well, 2 is a monomial. It's a power function. 2 is the same as saying
2 times x to the 0.
exactly 2 times x to the 0, right? So that's going to be, what's 0, even or odd?
Give me 1 second to equal it.
No, you don't need to. Just think of the pattern.
Because it's even enough.
It's even, right, because of the pattern. 2, 4, 6, 8. If you go backwards, you go 2, 0, negative 2, negative 4. It's even, right? Even numbers are the integers that are in between consecutive odd integers. So by definition, negative 1 and 1 are both odd, so 0's got to be even, right? So that's an even function.
Isn't that definition a little bit circular, because when you define odd numbers as the in between individual and even numbers?
But that's not circular, because it works the same in both cases. That's how you can prove that 1 is odd, because it's between, it's between 0 and 2, right?
Because when we do it, then you would prove that 2 is even because it's in between 1 and 2 and so on and so forth.
Right.
Isn't that circular?
How? How's that? I don't think so. I don't see how it is. If I know 3's odd because it's between 2 and 4, right?
You mentioned 4 even.
Because it's between 1 and 3.
And on we
Right.
go.
And on and on we go, but there's only one that we had to question, and that was 0, right? Okay? So, I don't see it as being that way. But either way, I mean, we're making a mountain out of a molehill. 2 is, or x to the 0 is an even function, because 0 is an even number, okay? So while we're talking about that, what about rational functions? I think I mentioned this once before, right? Rational function is a ratio of polynomials. This is kind of good to know. So if you can classify, like if I've got r of x is p of x over q of x, where p of x and q of x are polynomials, right? I can use that same rule I just discussed. If p of x has only even powers, then it's even, right? If it has only odd powers, it's odd. If it has a mixture, then it's neither, right? It has to be exclusively even powers of x or odd powers of x. But if the top is even, let's say, and the bottom is even, what's the rational function? What's your intuition tell you?
Even.
It's even. If the top is odd and the bottom is odd, what do you think?
Also even.
Even. If there's a mixture of the two,
Neither.
no, it's odd. If one's even and one's odd, or vice versa, it's odd. Yeah. That always works. That's kind of a cool thing to know. It
It's the
always
same
works.
thing with negatives and positives.
Yeah, it acts like negatives and positives. Yeah. Okay. So then this one right here, we could make this a little easier, couldn't we? We could turn this one into, so we're going to end up with minus. We get 0 minus the integral of 2 dx from 0 to 7/2 pi, and then we just need to put a 2 out front, right? Okay, which makes it easier to evaluate, right? So we end up with our answer is just going to be, so we just get, what's the integral of 2? 2x times negative 2, so we just get negative 4x evaluated from 0 to 7/2 pi. Well, at 0, we're going to get 0, right? So our answer is just going to be negative 4 times 7/2 pi, whatever that is. Right?
14 pi.
Yeah, it's 14 pi. Negative 14 pi. Okay? So my point being, why did I pick this example? Just because you can take advantage of the symmetric limits here, right? Breaking it into pieces. Okay, what about this? So somewhere you got that sheet I gave you with the integrals, but you don't need it. You can just play Calculus Jeopardy. What's the derivative of what? Playing Calculus Jeopardy. Derivative of what is secant tangent?
Secant.
Right, does that make sense? Derivative of secant is secant tangent. So we know that, the antiderivative here is secant x, and we're just going to evaluate that from 0 to pi 6. In other words, the answer is just going to be the secant of pi 6 minus the secant of 0, right? That's our answer. We go to unit circle and figure that out. Right? So at pi 6 up here, the coordinates are what?
Square root of 3 over 2.
All right, we got a big X,
1/2.
small y, and then here we're just 1 to 0, right? So secant is reciprocal of cosine. Cosine's the x coordinate, right? So the reciprocal then of the x coordinate is going to give us 2 over root 3 minus the reciprocal here is just 1. That's my answer. Okay. That's the area. I know we got a radical on the bottom, but we could rationalize it if we wanted to, right? But that's the area. Okay? Make sense? Okay, what about this? So this don't say anything out loud here. Let everybody think about this for a second. So we got to play Calculus Jeopardy with this one too, right? The derivative of what was 1 over x? Can you ever think about that? We we had a standard form for our derivative. The derivative with respect to x of something equaled 1 over x. Natural log, good. Yeah, we had natural log, right? Very good. So if we flip that around then, that must tell us that the integral, we're going to flip it around, right? The integral of, and instead of saying x's, let's make them u's. So the integral of 1 over u du must equal natural log of u, right? Okay, but there's one thing we got to be careful with there. Going back to pre-cal, what's the domain of a natural log function?
Greater than 0.
Right? Has to be greater than only positive values, right? So because the domain of this function is only values greater than 0, we have to do this. We have to include an absolute value bars around u. Now sometimes it's very clear that the argument of that log is non-negative, and so we don't have to worry about it, right? Or it is always positive, so we don't have to worry about it. In some cases, we do have to be careful to specify that, because once again, we have to make sure that we're only inputting values into the log that are in its domain, right? Okay, so we've got, here's the antiderivative rule that we're going to use on this one. Okay, so let's try to tackle this integral. What can we do here? One thing that would probably make it easier would be to do what? That 4.
So take it out front.
That makes sense. It's just a constant. 4 over x is the same as 4 times 1 over x, isn't it? Right. So we could take the 4 out front, and then I've got the integral of 1 over x dx from 1 to 9. And a lot of times what we'll do here with this one, this way, I don't really like to write it this way. I'd write it like this: the integral of du over u, right? So it just looks like a ratio. Later on, that'll be helpful, I promise you. Equals natural log of absolute value of u plus c. Okay. So then, what's this become? What's our antiderivative? Oh, there it is, right? We get natural log of absolute value of x. But we're doing a definite integral here, right? So we don't need the plus c part. All we need is the integral. Okay? And then we're just going to evaluate that from 1 to 9. Okay? So do we need the absolute values on this one? How come?
They're positive values.
Because we're only looking at the area under this curve from positive 1 to positive 9. And so we don't really need them here, right? And so what we would do is we would just take those absolute values and turn them into parentheses. And we actually should do that because it reminds us that we don't have to worry about taking an absolute value. Right? You only really want to include them when you need them. Right? And so we end up with then, we get our 4 times the value of the function at 9, so the natural log of 9 minus the value of the function at 1. 0. So, right, so the log of 1 is 0. So we just end up with 4 times the log of 9, because we know that the log of 0, or the log of 1 is 0, right? And the log of 9, we could simplify that a little bit using properties of logs. I mean, that's fine. That's the answer. What could we do using properties of logs that would make that a little easier? We'd always like, with logs, we'd like to write the number stuck inside the logarithm. We'd like that to be as small as possible. So because 9 is a perfect square, right, we could write this as 4 times the natural log of 3 squared, which becomes, what do I do if I have an exponent?
Bring it up front.
Is that right? Use that property where we bring the exponent out front, so we just write this as 8 times the log of 3. Okay. Question?
So how do you know, like, what's to stop you from turning the x into a negative 1x on top? Do you have some answer? Or
If you, say it again, if you were,
so you plot, you put a negative, or x to negative one.
Well, no, you could, but, and you're thinking just use power rule, right?
Yeah.
Okay, but power rule's not gonna work for that. That's a good question, I get where you're coming from. But if we tried to do that, right, if we tried to apply our power rule, so we could rewrite this as 4 times the integral of x to the minus 1 dx and use our old trusty power rule, that's just gonna give us, you're thinking, it's gonna give us x to the negative 1 plus 1, that's x to the 0 divided by 0. See the problem? The power rule falls apart for that one. Okay? Because you can't divide by 0. Okay? So that's, that's just it's just one of our standard forms. It's on the list, but you guys can see where it comes from. It just comes just from reversing the derivative standard form we had earlier. Okay? So I want you to see a log 1, and then finally, I guess we have maybe 2 more. So what about this? These are easy, right? So let's say it out loud here. Just think about this. The derivative of what is e to the x? So we ought to be able to turn the derivative with respect to x of what equals e to the x. Right, this is what we e to the x, yeah, exactly. So if we flip that around then, the integral of e to the u, or e to the x du, is just e to the u. And we've got to put our plus c at the end, of course, right? Okay, so the integral of e to the x dx is just e to the x, but because we've got limits of integration, it's a definite integral, we're just going to evaluate that from 0 to log 9, right? So we just get e to the log 9 minus e to the 0 is our answer. What's e to the 0? Anything to the 0? 1. Okay. And then e to the log of 9 is what?
9.
Right? Because if we exponentiate the log, they undo each other. So we just get 9 minus 1 equals 8 is our answer. Okay. And then I guess that's it. Okay, so I'll give you an option here. You guys decide. So that kind of gets us through up through 4-4 practice 3. Okay. Do you want to add a little bit extra today, or do you want to push that off? I don't care. I mean, I'm willing to. I don't care. I can either kind of go through a little bit more today, so you then can give you more time later to not do anything, or work, and or do you want to spread it out? Because I've really just got like probably about 4 more topics I just want to cover. They're not huge topics, but they're just little things I want to get through. So you can decide when you want me to do it. I don't care.
We keep going with that.
Yeah. Okay. I think that makes sense. Okay. All right. So mean value theorem, and this is pretty interesting stuff. This allows us to solve a kind of a good problem, interesting problem. What is, if I wanted to define an average value of some function on an interval, how might I do that? Right, we're used to taking averages where we add up, we can take a regular old arithmetic average where we add up a bunch of things and divide by the number of items, right? But how would you find the average value of a function on an interval? So here I've got this function f of x. How do I know what its average value is on the interval from x equals a to x equals b? I mean, you can probably think of different ways you could maybe define an average there, but let's see if we can come up with one that makes a lot of sense. Okay, and one way to think about this would be, let's look at kinematics. Physics gives us a really good way to understand this, right? If we took let's just say on the y-axis, what if we were measuring velocity versus time? So from your physics class, what's the meaning of the area under a velocity time graph?
How velocity changes over time.
No, it gives us something specific that's useful.
Acceleration.
What is it? Okay, almost. It's displacement.
Yeah.
right? So, I mean, that's kind of probably what you meant. So the area under a velocity time graph is displacement. So let's just say we've got this story here. Now, if you look at this graph, if I'm graphing velocity versus time, it looks like we start with a certain velocity, we accelerate up to a higher velocity, and then we begin to decelerate down to some minimum velocity, and maybe start to accelerate a little bit at the end. After we've done all that, the area under this curve represents our displacement, right? So if we want to understand what the average value of the function is, and in this case, the function is velocity, right? Well, what would you do? I mean, think about that situation. How would you define your average velocity on that interval then? If, say, I started at, we could even put some numbers on this, right? So let's say I started at let's say we started at 0 and we ended up at 10. After 10 seconds, I had gone some certain distance and my velocity varied the whole time, nonlinear, right? How could I maybe define what my average velocity was for that trip?
Delta D over.
Yeah, I want to get somebody else to answer a question. What do you think? How could I come up with a way to define my average velocity? Hypothetically, let's just say that over the course of this trip, we went 100 meters. Yeah. Okay, we could just take the total displacement, 100 meters, divided by the total time, which is 10 meters per second, right? So I would accomplish the same thing by starting off at some initial speed and speeding up and slowing down and coming to the end and covering 100 meters. I would accomplish the same thing by going at my average speed of 10 meters per second for 10 seconds, right? So what would that look like? What would that graph look like, my velocity time graph, if I just went 10 the whole time? Well, let's just say hypothetically that that's 10 meters per second. Isn't the area under that curve, the function's going to be a constant function. So it's a horizontal line, and the area under the curve is just going to be described by a rectangle, but the areas would be the same, right? That's the point. My displacement is the same. So doesn't it make sense then, if we want to define an average value for a function, wouldn't it make sense to think of that average value as just being the area under the function divided by the width of the interval? That's what we did, isn't it? The area under the function was our total displacement, and the width of the interval was just the time interval over which we traveled, right? Okay, yeah, that's a general way to approach this. Okay, so then, if that's the case, here's a way that I like to tell people to visualize that. So imagine that we extend the sides of the interval vertically upwards. So we're going to contain everything under the curve. And let's say that this curve has it's going to be modeled by some fluid that's frozen. Say it's ice. Okay, so we've got this little bit of, between these two plates of glass, I've got this frozen bit of water that's frozen in this shape. Okay, so maybe it's just a really thin aquarium. Looking from the side, that's the shape. We froze it instantly, and a wave was just zapped and frozen. Okay, if I want to reconfigure the area of this thing, what if I just melt the water? If I just melt the ice, what's going to happen to it if I melt the ice? What's going to happen to all this ice up here?
It'll level out.
Yeah, that's above the average water level, right? So everything that's above its average is going to melt, and it's going to fill in the divot left by the ice down here, right? And when this ice turns into water, it's gonna look pretty uniform. It's just gonna look like looking at a fish tank from the side, right? It's just gonna be a rectangle, okay? That's the mean value theorem for integrals. This is a big one in calculus, mean value theorem. It just tells us that the average value of some function on the interval from A to B, sometimes we call that f bar. You put a bar over a variable, especially in physics. It means average value. So the average value is just going to be the area under the curve divided by the width of the interval, right? So probably a better way to write that would be like this. The integral of f of x dx from A to B divided by b minus a, the width of the interval, right? That's it. Okay? And so the mean value theorem goes one step further. It says that if the function's continuous on this closed interval, so if I can draw the function without picking my pen off the board, then it also tells us that there's got to be at least one place on this interval, at least one, where the function passes through its average value, where it has its average value, right? Doesn't that make sense? In the context of our story about velocity, if I started off speeding up, so I got to some high velocity, and then I slowed down and got to some low velocity, well, wouldn't you agree that if my average was 10, there had to have been some parts where I was going faster than 10 and some parts where I was going slower than 10 in order to make the average 10, right? So somewhere in there, there has to be at least one place, and here it is, in between the endpoints, where the function has its average value, and we just call that C. Okay, so it guarantees the existence of at least one place where that's true. Okay? So these are the kinds of problems that we'll end up doing. Okay? And they're not hard, but it's all, if you get that concept, they're really simple. And on a lot of these, I don't care if you use technology. I just want you to know, what the mean value theorem is and how to apply it, but use technology to even evaluate the intervals. That's fine. So find the average value of f of x equals 4 minus x squared on the interval from -2 to 2. Okay, well, how would we set that up? So we just remember, all it is, average value is just the area under the curve divided by the width of the interval, right? So we would just say then that, that f bar, or if you want to call it f of c, in the language of the mean value theorem, it's just going to give us the integral of 4 minus x squared dx from -2 to 2 divided by 2 minus -2, so divided by 4. Right? Okay, and if we look at that, so there's 4 minus x squared, right? And if we want to add up, I can use Desmos or I can use my graphing calculator look, I can just say, if I define f of x up here as 4 minus x squared, then the integral of f of x dx from -2 to 2, look what it does. It tells me the answer, right? On Desmos, here's kind of a cool little trick too. If, like say in a college test, you can use technology, but you want to be able to put in an exact answer. Here's a way to kind of coax the exact answer out of Desmos. If you just go 10 point and then just put a whole bunch, you see the pattern. Just extend that repeating pattern out on the fraction, and then click on that little box. 32/3 is the exact answer. Okay. On your graphing calculators, you know how to do that, right?
Yeah,
Oops.
fraction.
Yeah. Okay, I'll make sure everybody has seen this. So you go. So on your graphing calculators, all you'd have to do is just go to the math menu, and you're going to go down to you're going to go to finite, so finite integral, number 9. You choose 9. It gives you the integral sign. So you're going from -2 to +2, and our function wasn't it 4 minus x squared?
Yeah.
And then I got to put the dx in the end. And it gives me back that answer, right? So now all I got to do is if I go up and grab that answer, and I just hit math, convert to fractions, so math 1. Okay, now it didn't do it. It didn't do it, how come? Because it was rounded too far. That's why. So I would have to do the same little trick. I'd have to do something like 10.6 and just go clear out. This seems kind of hokey, but it's how you do it. And then now I think this will work. Now if I go math, convert to fraction, yeah, there it does it. Okay. It does seem kind of cheesy to have to do that, but that's how I do it at least. Maybe there's a better way. I don't know if there is. Okay, so then you can kind of see this. Oh, that's the wrong one. I'm getting these mixed up, darn it. Oh man, I got about a billion. Okay, so then here's our function, and this is, I haven't done this yet, but I'll put all these up. I'll put links to all these if you want to play around with Desmos and kind of, this gives you a starting point. You can kind of just see how to do some of this stuff. So here's our function, f of x equals 4 minus x squared. If we want to take a look at the area under that curve, there it is, right? We can sort of visualize it, and we already know the answer is 10.6, repeating, 10 2/3, 32/3. If I make a new function that's equal to, so the value of the function is constant and it's just equal to the area under the curve divided by the width of the interval, and I've just defined a as -2 and b as 2, right? So there's my function, right? I just get h of t equals 32/3, and I add up that area from a to b. You can kind of see that those are the same size, aren't they? And if we look at the values of the integrals, whoops, darn it. Go away. There we go. Oh, here it is. So if we look at the area under h from a to b, it also gives me back the same value. Okay, so you can just see visually at least that, there we've just melted the ice and it's flattened out and just made a flat surface. Okay. All right. Okay, so did we get the answer? Yeah, we did. So the average value was 32/3, right? Okay, so now where does the function have its average value? How would we find that?
Input into the function.
Close. How would I find where the function has its
Solve,
set it equal to? Yeah, good. So we just set the function equal to 32/3 and get an answer, right? So we end up with the equation 4 minus x squared equals 32/3, which you could all solve. But, once again, Desmos does this pretty easily, right? On Desmos, so if I just graph those two values, if I just graph the two functions, there's f of x, there's my average value, if I just find out where they're equal, at least as decimals, I can figure out what the points of intersection are, right? So those are the places within our interval between -2 and 2 where the function has its average value. If you want an exact value, you just got to solve the equation algebraically. Okay, question? Comment? Okay. All right, so what about something like that? We want to find where this function has its average value, or find the average value. I'm just going to do the integral of my function. Right. So what's the antiderivative of sine? Negative cosine. I can pull the negative out. I'm going from 0 to pi minus 0. So on the top, that's just going to give me minus cosine of pi minus cosine of 0, right? Well, what's cosine of pi and the cosine of 0? So we're going to get cosine, so we're going to get -1 minus 1 over pi, so I'm going to get what? 2 over pi? Anyway, you get the idea.